discuss on the process of flow for the pack designs. Now, since we have gone through a lot of understanding on the basics of cell, module configuration, series and parallel combinations, C rates, life cycles, voltage windows, etc. Now let us focus on what is the process flow for the pack. So step 1. Since we have seen a case study on how the battery pack requirements look like, and from the battery pack requirements we need to choose the right cell that is to be selected for the application. So this application is mainly for bus and car, and it's a high voltage application, and we have to choose it accordingly in the right way. And then after the selection of cells, we need to consider the battery pack voltage and capacity, which we have done, and then we are going to combine the cells in a module in different series and parallel combinations. But over here, when we have to make modules, we'll have to pay more attention that all the modules are of same voltages and capacity, so that for example, if we have to get a 60 volts as nominal voltage with 100 H capacity, the preference would be like we'll have to connect 4 modules of 15 volts and 100 H each, so that we'll get a 60 volt. So that is something which has to be taken care of. When we make a pack, all the modules should be equal, and yes, the module consists of several cells which are to be connected in series and parallel, and that has to be rightly chosen. So the most important factor for this whole pack, which is the cooling design. Now we have modules in place, we have cell configuration in place. These cells are of high capacity, high voltage applications, so they dissipate a lot of heat because there are a lot of charging and discharging happen. There are a lot of heat being generated, and with such amount of heat being generated, it's very important to extract the heat. Therefore, the cooling design calculations has to be intact. So which means, as per the rise in temperature, the cell which generates heat has to be extracted through a right cooling mechanism. And for high voltage, preferably active cooling is used, where we have a cold plate. As we have talked earlier, we have a cold plate and there is water flowing through the cold plate, and the cold plate extracts the heat accordingly. So the flow rate has to be right, the material used has to be right, the module to cold plate contact has to be the right way. So all these things are playing a very essential role in choosing the right cooling design calculations, etc. And apart from that, we have a lot of electronics, wiring harness designs. So when we say electronics, we have BMUs, we have VCUs, we have cell-to-cell interconnections, which is through bus bars. And there's also a very important part, like when we have a bus bar, the contact resistance has to be as low as possible. That means the weld joint has to be good. So that is one. And then we have wiring harness design, which means we have wires of different diameters, lengths, etc. And we need to see that there is no voltage drop, there is no overheating of the wires. We need to choose the right wire appropriately. And then one tip over here is like the pack is usually a combination of a lot of modules connected together. It could be in series to achieve the final voltage, or it could be in parallel connections or module. Usually we should be avoiding the parallel connection to avoid any string controllers need, etc. So that is one tip which we could always see, that let us make sure that the modules are always connected in series, so that we keep the parallel combination of the cells at module level only. So that is something advantageous to us when we go at a pack level, so that we only have series combinations, which would make the whole life easy. Instead of 10 modules we series it, and then we have another 10 modules we series it, and then we connect them in parallel. It's going to be a huge confusion, and it's not preferable when we do a bulk production in such way. So these are the 4 steps which are to be considered when we do a pack design. How do we define the process for the whole pack design? Now we'll go back a little bit into module design considerations. So here we'll understand, since we have 3 different form factors, cylindrical, pouch and prismatic cell, which are arranged in series and parallel combinations, we'll try to understand what does each of them have. So over here, the first one is for a cylindrical cells. So here we have cylindrical cells which are arranged in series and parallel combinations, where we see a cylindrical cell with a capped side, which is this one. It's a positive side, and we have a plane area which is negative side. I believe cylindrical cell is something which you might have seen daily almost. So this capped side is usually the positive cell. So if you see the next image, we see that there are a group of cells which are placed with flat heads on the top, and also there are a group of cells which are placed with capped heads on the top. So which means they are placed in zigzag arrangement. So which means for series combination, you need to connect one cell of a positive to the negative of another cell. That is how you get a series combination, like positive of one cell is connected to the negative of another cell. Here is what that we see in the image, like the groups have negative side facing, and when we have positive side facing on the top, which are put together. So which means we are going to connect them through a nickel bus bar. So the bus bars usually used for cylindrical cells are nickel. It could be a copper or coated with nickel. So these are the bus bars which are used. So here if we see, we have a common group cells. So we have 16 cells like this. We have 16 cells for the positive, which means here the 16 cells are in parallel. So which means we have 16 into whatever be the capacity, like 16 into 1 Ah cell, we have 16 Ah, which means the pack capacity becomes, or the module capacity becomes 16 Ah. And since we have 1, 2, 3, 4, 5 cells, a 5s combination, like we have 1s, this is 2s, this is 3s, this is 4s, and this is 5s. So this whole of them are arranged in 5 series combinations. Each string or each group has 16 cells, and 16 cells are of the positive side are also arranged on the same side. And now like that you have 5 groups, so that you connect one group to another group becomes 1s. When you connect second group to the third group, it becomes 3s. Next it connected becomes 4s. Then when you connect it to the last group, it becomes 5s. So you have 5 cells or 5 groups connected in series, with each group having 16 cells connected in parallel. That makes it a 5s 16p configuration. This is how a module has been configured. That means over here, let's take a typical capacity. We have a cell which is from 3H to 5H capacity, and form factors are anything 18650, 21700 or 32600. So as I was mentioning, 18650, the first two numbers over here, the first two digits represent the diameter of the cell, and the next two digits 65 represent the height of the cell. So the capacity of a single cell is smaller, so we have several cells have to be connected in parallel, which is to achieve a 200 Ah we need to have 5 Ah cells of 40 numbers connected in parallel. So this is how you get a cylindrical cell in parallel combination. See, just imagine 16 cells connected in parallel to get the required capacity. So this is how you make a module. You put all the cells where you wanted to get the capacity, you put all them in parallel first, and that becomes a string. You connect all the strings, positive negative of each one string to another string with the positive negative of those strings. You get a series combination. So this is how a cylindrical cell module is designed. So now we see exploded view. So over here, if we see an exploded view of a cylindrical cell, we have a cell holder or a heat sink. Usually a heat sink is used so that when the cells go inside, all the heat is extracted well. So you have cells going into the heat sink, and then you have cell to cell interconnection. These are the nickel bus bars used, these pink ones. These are the nickel bus bars used. And then over here, this brown portion is something that acts as an insulator, so that these bus bars do not touch the cell body, because the cylindrical cell casing is a metal body. It's a metal can, so that you insulate it over that first, and only the required portion is exposed, and that is where you connect the bus bars and weld it. And then you have a sealing gasket, so that there is no ingress. Once you put the sealing gasket and then you put the enclosure, there is no water or any dust entering into this whole pack. And then you have a wiring harness. So this wiring harness could be a PCB or sensor wires, voltage wires, etc., anything, so that you connect each sensor to each cell, and then you monitor the voltage or temperature of the whole unit. And then you have electrical isolation pad, because there is current carried everywhere. You need to isolate all the exposed body of the cell, so that this is the battery pack enclosure which is in contact with the cells of the bus bars. That portion has to be insulated well, so that when somebody touches the battery pack externally, the current is not flowing through that. So you need to isolate all the parts, or you need to give a proper electrical isolation to all the electronic parts internally for the battery pack, so that there is no current or open circuit voltage flowing through the enclosure of the battery pack. It is common for anything. It has to be common for cylindrical cell or a pouch cell or a prismatic cell, that this is some care which has to be taken very appropriately.
Or else, if there is any floating current going on, there should be shocks to the people sitting near to it or people touching it.
So that could lead to electrocution. And now we'll discuss on pouch cell. Now the earlier one was cylindrical cell, where we saw a lot of cells connected in parallel, which is called a string. Then such strings are connected in series, like positive of that string is connected to a negative of the other string, and then that becomes a series combination. Just you saw how many cells are involved there. Whereas when we see a pouch cell, it is quite easy. Now if you see, there are just 4 to 5 cells, and this each cell capacity itself could be 20 H to 65 H. But what happens is in prismatic and pouch cell, as we discussed, that these cells tend to expand over a period of time while charging and discharging. So here is what we see, where we have a pouch module, where we have more parts of it. We have a metal plate, we have a bottom plate, we have a thermal insulation, right? These are LTO cells, and there are a lot of BOM parts that get added to this. And though the capacity of this cell is bigger when compared to a pouch cell, maybe the number of cells needed would be less, but the number of other parts needed to assemble would be more. So one thing is, in this pouch cell we use metal plates in between. So these arrows which are there, we put metal plates over there, which is preferably aluminium, so that the heat generated, because there is a lot of flat area lying over there, there are vacant spaces, the metal plate we can insert over here, so that the heat can be dissipated from the cells, which acts as a heat sink over there. That is in contact with the bottom plate, which could be a passive cooling system. So all these lines are basically the fins. So you put a metal plate which is in contact with the cell body, and that metal plate is in contact with the heat sink below, so that all the heat which is generated by the cell is conducted to this metal plate, and that transfers it to the passive cooling system, which is the heat sink below. And that's how you take away the heat as much as possible. So whenever you're charging and discharging the cells, the cell will generate heat, and to avoid overheating of the cells, you dissipate the heat in this way. So you can put metal plates, you can put any good thermal conductive materials, like you have thermal foams, thermal pads, thermal paste, anything you could put to dissipate the heat. But what happens is, if you do charge and discharge, these pouch cells tend to expand a lot. And when such expansion happens at a certain point of time, the cell bulges a lot and it could lead to explosion. So it is very important to hold the cell intact by applying pressures on both the sides. So you can put a pressure plate over here, you can put a pressure plate on the other side, and you fasten it tightly with a pressure plate, so that all the cells are put together. You're tightening them so that whenever there is expansion and contraction, the cells are not bulging as much as, because there's already a pressure acting, so the cells do not tend to expand a lot. So this is something which you need to consider, this complexity. There are a lot of complexities, but you need to do the right selection of design to make it safe. But still, there are certain advantages of this pouch cell, like you have higher energy density, the volumetric energy compared to prismatic cell is higher, and also because of its larger capacity cells available, the number of cells needed for parallel combination reduces a lot when compared to cylindrical cells. So this is something which you need to consider while making a pouch cell module. So and also what happens is, when you connect the cell to cell, the contact resistance by using a bus bar also has to be made sure that the welding is right, the welding is proper. So that is a challenge in cylindrical cells, because we have a lot of cells and you have a lot of bus bar to cell connections, and in such cases the welding has to be right, or else there could be a lot of contact resistance built up. And the same could be with pouch cells, but because the cells are less, you don't have much contact resistance added up because of less cells. So that is the advantage when you have with pouch cell. The same case when you see a prismatic cell. Prismatic cell over here is a little bit different. Now, if you see a pouch cell, which is very thin. So there are certain difficulties. When you have a thin pouch cell, if you want to extract heat, only this area, this flat area is the only portion available for you to extract heat. Because if this certain thin portion, this is like 12 mm or 15 mm, not more than that. So there is no way where you can extract heat from the side or from the bottom. But unlike that, you have prismatic cell which has a decent amount of thickness. Usually prismatic cells have a thickness of 28 mm to 30 mm or even more. It depends on the capacity of the cell. The bigger the capacity, you could see that the thickness of the cells are a little bit higher. So when such thing happens, when you have prismatic cell, just see the way the thickness of the cell is. You can directly put all the cells over here in a module, and you can use a side area for extracting the heat. So this is one great advantage that you will find with the prismatic cell, that you will have sufficient area. In fact, you don't need to put metal plates in between, and also find a path that is touching the external side plates so that you conduct the heat. So all that are gone, all that are not needed with the prismatic cell. The construction of the module becomes quite easy and it becomes quite effective, so that you have wide areas of thickness where you can extract heat as much as possible. That is one advantage you'll have with the prismatic cell module. But followed by some advantages, there will always be certain disadvantages. Now the prismatic cell has higher capacity, and these cells are to be connected, at least the parallel connections are gone, because you have higher capacities, you don't need to connect them in parallel. But the series connections are something which you'll have to do, ultimately you'll have to do at any point of time. But when that happens, as you know, the prismatic cells over here have different kinds of terminal tabs, positive and negative tabs. You can have a prismatic cell with tab welding option, or you can have a prismatic cell with a internal threaded option, or you can have a prismatic cell with tab with a screw. So when such kind of prismatic cells are used, you will have to connect the bus bar through nut and bolt. And with nut and bolt, there are a lot of tendencies that through vibrations or mechanical shocks they can get loosened, and when they get loose, the contact resistance builds up and there will be hot spots formed over there. Usually also, when we have a cylindrical cell or pouch cell or prismatic cell, when you run a thermal analysis, the bus bar tabs or the top portions where the current is being extracted, those are the hot spots. And when you have such not good joint between the bus bar and the cell with a nut and bolt, that can increase the contact resistance even more. So that is something which you have to consider when you have a prismatic cell in use. You will have to follow the right torques, right amount of force required for fastening the bus bar with nuts and bolts. So that is something which you'll have, but followed by there are a lot of advantages considering the thickness of the cell, where you can put thermal pads below on the sides and extract the heat directly from the cell to the heat sink or enclosure. And yes, you would also need a pressure plate over here, even though there is a aluminum can for a prismatic cell, but still you need some pressure plates so that the slight expansion or anything which can happen is arrested properly. Now we'll understand what are the different role of components in the battery pack. So in a battery pack you have different components which we discussed. So this is in general. So we have components like we have in making a module, like we need cell holders, which is basically to hold the cell. And when it comes to a pouch cell, this HCP we call it a heat carrier plate, so which is nothing but a metal plate which we saw in the earlier slide. So that becomes an integral part of the cell holder. So this becomes a unit, which usually a cell holder can be ABS material, and HCP is a heat carrier plate which is used for dissipating of heat from the cell. It is basically aluminium, because aluminium has lightweight and also it holds a good conductivity. So aluminium is usually used as a heat carrier plate for dissipation of heat from the cells. And then we have thermal foams.
Why do we use thermal foams over here? Usually these thermal foams are something which can expand or contract, which is known commonly to everyone.
So when the pouch cells are used, the pouch cells during charging and discharging, they also expand and contract. So when such things happen, there is some gap or void which forms. So when you use thermal foam between cell and a HCP, whenever the cell contracts, what happens is that extra space which it creates is going to be filled by the foam. And when it expands, since foam has a capability of taking the deformations, the foam takes over there. So this foam which is used has to be calculated, like you calculate such that the foam is compressed to only 30% or 40%, and you still have that 70% of elongation left with the module, so that whenever the cell is expanding and contracting, the thermal foam takes those changes in the dimensions or thickness of the cell. So now we'll understand what is the role of components in the battery pack. This is basically a cell block. We have a lithium-ion cell and we have a thermal pad which is placed on it. And this is how it can be a foam or it can be a pad. And then we have a cell holder which is coming on top of it. So this is how a lithium-ion cell forms. So we have all of it together. So now we have a prismatic module. So this is the same module which we have considered the cell of 3.2 volts 105 Ah. So with that cell we have made a prismatic cell module with the same prismatic cell, and now if we remember, that cell was of a dimension called 130.3 mm, and the width was 36.7 mm, and the height of the cell was 200.5 mm. With that, we have arrived at a module where each module will require 20 cells, and that means when we put the cells in a 10s2p configuration, that cell, each of 3.2 volts, when 10 cells are connected in 10 in series, will give 32 volts. And then when we have two cells in parallel, it would give a capacity of 210 volts, which means we have 20 cells connected in 10s2p configuration. Then the module of each would be 32 volts 210 Ah with a dimension of 790 mm, 136 and 220. So this is how we arrive at a prismatic module, and connecting all these modules in series combination would give the required pack level. So one important part over here is, you will be surprisingly, if you do a small math directly over here, which means you have 36.7 mm along the width, which is this, and you're putting 20 cells over here, your math would not tally. Because you're putting 10 cells, 20 cells into 36.7 mm, it would not give you 790. And similarly, when I just said the width of the cell is 130.3, but over here I have arrived at 136 mm. You'd be confused, how is this happening? It's not a mistake, it's not an error. And again, when I said height of the module is 220 mm, but the cell's height is 200.5. So where are these extra dimensions coming from? So these dimensions are coming from the extra BOM components which are involved in the prismatic module. As I said, this does not only involve cells only. The prismatic module consists of end pressure plates like this. We have end pressure plates, we have side plates, we have thermal pads coming in between, and then we have top cover for insulating the whole bus bars. We have bus bars coming in. You should be using cell holders for each cell. Well, there are a lot of other components which are coming into a module, so it doesn't just become the bare cells only. So there are a lot of other parts. So what are these? That will understand the calculations. So now from these slides we'll see what are the bare cell to module dimensions. So now we have module length, which is module length becomes 20 times of cell thickness, which is the thickness of the cell. That becomes the module length. So that means the thickness of the cell when arranged 20 cells together becomes the length of the module. But the module width remains the same. Module width is nothing but 1 times 130.3 is 130.3 mm. And the module height is 1 times 200.5 is 200.5 mm height. So these are the bare cell to module dimensions, but we have a lot of dimensions which are changing in this slide. If you see 790, 136 cross 220 mm, and we have 734, 130.3 and 200.5, it's different. So in the next slide we'll find out what is the difference coming from. So the module consists of thermal foam, which we have assumed to be 0.5 mm after compression. We have a cell holder which is 0.5 mm thick. We have a heat carrier plate which is 0.3 mm along the length. So when we put all these together, we have 26 mm. Module 1, which is 26 mm, is the extra module length which is coming when we consider all these thermal foams, heat carrier plates, cell holders, etc. And then we also have end plates which are coming. We have end plates, 2 numbers, each being 15 mm. That is the reason why we get 790 mm. The next one, module width. We have assumed 2 mm to be the width, which could be the cell holder and any other thermal foam used, and then that gets added up to the module width of 130.3, which gives us 132.3 mm. And then we have a bus bar height which is of 5 mm, and we add up to the module height, it becomes 205.5 mm, and we put a cover on top of it which gives the extra 10 to 15 mm needed. So all these 5 mm, 2 mm, 26 mm are all assumed dimensions as per the design simulations. All these values would definitely change if a proper analysis is done according to the cell available. So these dimensions would change, and the analysis drives all these dimensions needed. So these are just for information how these dimensions play a major role in deciding the module overall dimension. Now we'll talk about the selection based on the sizes and volumes. So over here now we'll understand the modules depending on the different size of the battery pack available. How do we fit into that? Now we have a battery pack which is having a length of 1700 mm. We have a width of 1750 mm and a height is along the Z axis, which is 0.3 meters, and we have 0.2 meters assumed, so I think we'll have sufficient space on the height. So if we see over here, now let us consider the volumetric efficiency of this whole thing. We have 20 modules, so the total pack volume is something around 0.89 meter cube, and we have a module volume which is 0.48 meter cube. So these are the module volumes which is available. So we have at least 60% of it still we have occupied, and we have rest 40% available with us. So those are the volume which has to be used for the other components. Like we have electronics, like we will place the BMU and BCUs over here. So then the green area over here represents all the contactors, power connectors, BMS, wiring harness used in this battery pack, and the yellow area over here represents the cooling hose pipes, the cooling line inlets, outlets, etc., which are required for fixing the cooling plate. And the cooling plate, mind you, would always be below the modules, so that the heat generated from the modules is taken away from the below portion. So that is the place where a proper contact has to be achieved between the modules and the cooling plate. So these are the selection. How do we separate the dimensions for the modules? How do we allocate the dimensions needed for electronics, etc.? It has to be at least 30% to 40% left, so that we can utilize that space for all these electronics, etc. Now we'll talk about what are the different requisites for having a robust pack. Now a robust battery pack should have certain qualities where it should be able to withstand vibrations and shocks. So to do that, that means it's not just the pack. This vibration and shock must be such that the module, when it is designed, the module should also be sustaining such kind of vibration. So usually in India we follow AIS standards, which is calling for at least 3G load vibration. So usually when we need to do this test for transportation, like means if we are shifting the pack from one place to another place, there is a certain standard called UN 38.3, and that calls for vibration level up to 5G or 8G. So imagine what kind of engineering you need to put into so that the module and the whole pack is going to sustain such kind of vibrations. So this means that all the enclosures, modules which are designed, all the mounting which you would be doing of the BMS inside the battery pack, this would be subjected to a constant phenomena of vibration throughout, when it's on the road, when it's on the train, or when it's being shipped, or when it is on the moving vehicle which is discharging. So anything, any loose contact, like any loose screws or anything, would make the whole pack stop, terminated. The BMS might terminate the whole pack because of any loose contacts or loose wires and all. So it is very important that when the whole pack is assembled, when it has to be assembled, the right torque values have to be used. One of the important consideration is whenever the screws are used for critical components like sensors and all, you could always use a thread sealant, so that with the right torque, which would hold the screw well so that it doesn't loosen quite often. And then the most important part, the next one, is the good ingress protection. This is something very important, like all the enclosures must be properly sealed. Like it has to prevent water, it has to prevent the dust entry, as these battery packs are used for the buses, which could be rooftop or chassis mounted. There is going to be a high probability of dust and water. And imagine being at any of the packs in India with all puddles and water puddles and non-uniform roads. The pack is going to be subject to a lot of vibration, and with that vibration, if your sealing ingress is not good, sealing ingress just damages, and then you will have all the water and dust going into the battery pack, which could first deteriorate the performance of the whole pack, and then it could also lead to a lot of catastrophic failures like short circuit, etc. can happen. And then the next important part is the thermal dissipation of heat. So all the cells over here generate heat during charging and discharging, and that has to be effectively dissipated as much as possible so that they are operating at optimal temperatures. Therefore, you need to design a very good thermal loop always, so that thermal loop will help you to dissipate the heat. And what does the thermal loop consist of? It's just that what we decided, what we saw earlier, like it should have a thermal plate, it should have a heat carrier plate, there is a heat sink which has to be calculated properly. All these calculations should be done. So these are theoretical, but when you do it in practical conditions, you need to take care that there are no air gaps formed between the cell, heat carrier plate, etc. That is something which you need to take care while doing a thermal loop design for thermal dissipation of heat from the cells. And then you need to have a very good electrical isolation for the vehicle body. So there has to be no live current coming from the electrical parts like the battery pack especially. So you need to select the right wiring, and you need to see that all those wiring and all the current carrying wires and all are shielded as much as possible. As we saw in the exploded view of the cylindrical module exploded, used an electrical isolation sheet where it will stop the bus bars in contact with the enclosure of the module. So that is how something you have to take. You can use any electrical isolation sheets, you can use silica sheets, mica sheets, or you can use any preferable coatings on the internal part of the enclosure so that they do not conduct electricity whenever bus bar or the cell is in contact with them by mistake. And then most important part is again the venting of gases, which is basically in case of cell failure, you need to vent out the gases as much as possible so that the pressure doesn't get built up inside the whole battery pack. And the pressure would definitely get built up into the battery pack because this battery packs are usually IP65 or IP67 sealed, and when such kind of pressure buildups with such sealing happen, it is very important to vent out the gases. So therefore you need to use breathing valves, vents for the battery pack enclosure. Whenever the temperature builds up above atmospheric pressure, this vents open up and they release the gases as much as possible so that the battery pack doesn't become an explosion bomb. And then communication. This is one of the most important factors for the whole battery pack. You need to have a seamless communication between the battery pack, which is the BMS, and which is the communication portion, and the vehicle control unit, where BMS would be translating all the information from the battery pack to the VCU so that the vehicle constantly knows what is the status of the battery pack. If there are any errors, the VCU would immediately communicate and take control, saying that you terminate the battery pack so that there are certain errors that has been triggered and you should not use the battery pack anymore. So such certain kind of communications happen between the BMS and the VCU. So this is the reference high voltage design pack, how it looks like. So as we saw, we have a lot of battery modules over here. There are like how many? 18 modules over here, and each module. So this is a slightly different design. If you see, the cooling plates are placed between the modules. So we have 1, 2, 3, 4, 5. We have 5 cooling plates over here. We have modules over here, and all the switch box and all the electronics are over here. This one of it is a battery management system. This is the lower housing system. So this is the lower enclosure. So basically there would be a top enclosure coming over it, which will be fixing the whole pack, which would be covering the whole pack. So this is how a high voltage battery pack would look like. Just imagine a lot of modules, all the wiring harness coming from this goes into the switch box at the top. It's over here. So this portion is the controlling part of the whole battery pack. So this is how the high level components of a battery pack would look like.